Swayam Prabha. Digital India. Educated India.
Okay, today we will be discussing about inverse kinematics, Jacobian and singularity, and in the very briefly to discuss about what we had talked about in the last class. We talked about the transformation matrix, how to get the transformation matrix from one frame to another frame, then DH parameters, how to assign access to a robotic system, and then from the DH parameter table how to use the generalized matrix and then get the different transformation matrices. And after you multiply the transformation matrix, we can ultimately get the relationship between the end effector coordinates or the frame attached to the end effector to that with the base coordinate frame. So after you get that, what we need to do is, in inverse kinematics, we need to find out what is the desired position and orientation of the end effector and what are the corresponding angles which will take you there. So very briefly, going into what we discussed in the last class is essentially we talked about inverse kinematics, and the general procedure for doing the inverse kinematics for any robotic arm is first use DH parameter, use assign frames to the axis to each of the joints of the manipulator, and then write down the DH parameter table. After you make the DH parameter table, using the DH parameter table, find out the transformation matrices which is going to go from which gives the relation between the different joints. So this one gives the relation of axis 1 to axis 0, this one gives the relation between axis 2 and axis 1, like that up to t n and n minus 1, which is the last frame. So using the DH parameter table, we can use each row of the DH parameter table and put it into the generalized matrix and get each of these matrices which correlates the frame, one frame to the previous frame. Now once we get each of these matrices, what we need to do is to multiply them and get the final matrix 0 to n. And how do we get that? We simply multiply 0 to 1 into 1 to 2, like that until the last one, n minus 1 to n. Okay. Now so this gives us the relationship between the last frame, the end effector frame, and the base frame, 0 frame. Then what we do, this one you should remember is a 4 by 4 matrix. Okay. So after this, what do we do for our inverse kinematics? We equate this matrix, we equate this T0 to n matrix with the matrix which gives us, which contains the desired position and orientation of the end effector, desired position plus orientation of the end effector. So this is also a 4 by 4 matrix. So on this side you have a 4 by 4 matrix, and this side you have a 4 by 4 matrix. So what we do is we equate term by term and then try and solve. Now as we saw in the last class, if you look at the matrix for this very simple case of this 3-link system, 3 degree of freedom planar system, the end effector, the total transformation matrix that comes out, this is my axis 1, joint 1, 2 and 3. So the one that comes out 3 to 0, if you remember what we did in the last class, this matrix is of the form 1 2 3 minus sine 1 2 3, this is sine 1 2 3, cos 1 2 3, 0 0 1, this is 0 0, and here you have L1 cos 1 plus L2 cos 1 2 and L1 sine 1 plus L2 sine 1 2. And this would be 0, this is 0 0 0 and 1. So for this manipulator system, the third relationship between the third frame and the 0 frame is given by this matrix. Now we take this matrix and equate it to the matrix of the desired position and orientation. So this is my desired, let us call it desired position plus orientation matrix. Now this will also be a 4 by 4 matrix, and whatever is the desired position will come here. So this is the desired origin x, y and z of my frame 3 will come here as x, y and z, and whatever is the rotation matrix will come here in the terms of R11, R12, like that, and there will be one more column and one more column here, right. So, what we do is we equate this matrix to this matrix and then try and solve. Now, what are the unknowns? The unknowns are here theta 1 and theta 2. Okay. So, theta 1, theta 2 and theta 3 are the unknowns, right. So, what we basically do is we do not try and equate terms from here to here, okay. That means the rotation part, but what we try and do is we try and equate from this side which is the distance between the two origins. So, I simply equate L 1 cos 1 plus L 2 cos 1 2 is equal to x and L 1 sin 1 plus L 2 sin 1 2 is equal to y. Then we square and add, and then now, so what happens after squaring and adding, essentially I can find cos theta 2 is equal to x squared plus y squared minus L 1 squared minus L 2 squared divided by twice L 1 L 2. So, L 1 L 2 are the link lengths L 1 L 2, this is angle theta 1, this is angle theta 2 and that is angle theta 3. So, once you from here we can find sin theta 2 as 1 minus root over cos squared theta 2, and we use the function a tan 2. So, theta 2 is equal to a tan 2 sin theta 2 and cos theta 2, and this is essentially done to get the two positive values. So, something to remember here is that essentially, because this is sin and cos, for sin and cos we will be getting two solutions always, or two values which will satisfy the same xy coordinate, and this is something we explained that was explained in the last class, that if you, this is one solution. So, for a given x and y here, for a given coordinate x, y and z, for this solution this is one set of solution theta 1 theta 2, the other set of solution is here, which is this one, which is theta 1 dashed, and that is a minus theta 2 there. Okay. So, both these solutions will give you the same position there, because of which we have to be careful that we take only the positive values. So, the positive values will give you this value and that value, and what is going to be the other value? The other value, the other solution, I mean, it is going to be this one theta 1 dash and a minus theta 2 there. So, we get two solutions for every x, y and z, and hence we do not take a cos inverse here. We basically convert it to this a tan 2 function and then use a tan 2 to get cos 2. And once we get cos 2 from geometry, we can get cos 1 from geometry. So, this was done in the last lecture, that we can find theta 1 and theta 2 basically from theta 2 comes from here and theta 1 comes from geometry. So, we can find these two solutions. Now, this is essentially a recap of the procedure for finding inverse kinematics, and the procedure for any manipulator system is the same. Okay. Now, so the procedure is assign frames, find DH parameter table, find the transformation matrices, multiply them out, then see the final matrix which relates the end effector to the base and equate it to the homogeneous transformation matrix giving the desired position and orientation, and then try and solve equate term by term and try and solve. So, if you can solve, then we are lucky, and if you cannot solve, then it is too bad. And I also said that when we say a solution, we basically mean a closed form solution. So, these are not numerical solutions. Okay. So, they have to be a closed form algebraic solution or by geometry. So, let us proceed a little bit today and look at a bigger manipulator. Okay. So, this 2 degree of freedom arm that we just solved is very simple. Okay. It is planar and very simple, just to understand is okay. But then a real robot would have 6 degrees of freedom, or it will have more. So, let us today look at the kinematic solution of 6 degree of freedom. So, this is a 6 degree of freedom PUMA robot. The name PUMA basically means primary universal machine for assembly. So, it is primary universal machine for assembly. That is where the name PUMA comes from, and this was made about 1960 by the company Unimation. Okay. So, the Unimation company 1960 made the robot PUMA, and the structure of the robot is almost similar to that of the human hand, human arm, and so it has a waist. So, it has a waist axis, it has a shoulder axis, then it has an elbow, and it has a wrist consisting of a roll, pitch, yaw. So, there is a roll, pitch and yaw at the wrist. Okay. So, it is 3. So, 1 1 1 and 3 at the wrist. So, it is a 6 degree of freedom system. Okay. And so this is what the PUMA robot looks like. So the waist of the robot is an axis, it can rotate about this axis, okay, that is called the waist. Okay. The shoulder axis, so this is a vertical axis similar to our waist axis. So this is going to be my first axis, Z0 and Z1. The second axis is here, which is my Z2. So this can be looked upon as our shoulder axis. The third axis is here, which is my elbow axis, which is Z3. Now Z4, Z5 and Z6 are given here. So Z4, Z5, this is Z5 and Z6 are given at the wrist. Okay. So it has 6 degrees of freedom. The first one is this axis, second is this axis, third is rotation about the elbow, fourth is rotation the roll axis, which is here. This is the pitch axis, and that is the yaw axis. Okay. So this is a 6 degree of freedom robotic system. And if we draw the axis assignment now, let us assign the axis and then find the DH parameter table. After finding DH parameter table, we will then find the transformation matrices and then find the relationship between the last frame, which is given here, that is my 6th frame, to that of the 0 frame. So let us start off by, let us understand the working of this first. So first is there is a 0 axis here. So 0 and 1 axis can rotate about this, that is my 0 and 1. The first axis is along this 0 and 1 we can take it. So this is my waist axis. So let us assign 0 there and 1 there. So it can rotate like this about the waist axis, which is here, the total axis. The second axis is the shoulder axis, which is this one. So this is my shoulder axis, which can call it Z2. The third is an elbow axis, which is Z3 here, okay, and this part is shown here, okay, for clarity. Okay. So Z3, now you come to the this part of the front part of the link, the forward link, that is here, and my Z4 is this axis, which is the roll axis. So this is Z4, Z5 is in that direction, okay. So that is Z5, which is the pitch axis, and then Z6 is again here, which is the yaw axis. Now once we have put our the Z axis, now let us put our X axis. So something to note here is that Z0 and Z1 is in this direction, Z2 is here. So there is a 90 degree angle there, okay. Z2 and Z3 are parallel. Now Z3 and so in this figure, where is Z3? Z3 is in that direction, okay. Now Z3 and Z4 are again orthogonal, okay. So this is my Z3. So Z3 and Z4 are again, Z4 is in this direction, so there is an angle there, okay. Again Z5 and Z4 are orthogonal, and again Z5 and Z6 are orthogonal, but they intersect at the same point here. So from here we need to put in our X axis. So let us make the let us assume that the origins of Z0, Z1 and Z2 are the same point here, okay. I could have taken Z2 origin here also, okay, there is nothing wrong in that, but just for simplicity we have put our origin here, and let me say the X axis is in this direction, okay. So this is X0, X1 and X2, okay. So the X axis, as we said when assigning the DH parameters, that if the Z axis are intersecting, then the X axis is perpendicular to the plane containing the Z's. So if you look at the plane, this is Z1 and that is Z2. So this is the plane which is, so that plane is the one where the Z's are intersecting. So the X axis is going to be perpendicular to this plane containing the Z's, and hence X2 is this side. Now because X2 is this side, X1 and X0, X1, X2 we can put it together, okay, just for simplicity. What about X3? X3 we can put it in this direction, okay, that is my X3. Then we can go to X4. Now X4 we can put it upward, okay. Again the same logic, that Z3 is in this direction and Z4 is in this direction, okay. So they are contained more or less in a plane there, and so we take this, so this is not a plane, but we take X4 to be perpendicular to the Z4 on this direction. Now Z5 is that side, so we take X5 also this side. So I get X4, X5 and X6 to be the same axis in the same direction. So you can see that X4 is here, X5 is here and X6 is here, okay. So we can take it as the same axis. Now looking at the correspondence of the PUMA robot to that of the human arm, I will just explain with respect to the human arm, because it has the same structure. So essentially the human arm has a waist axis which is here, then there is a this is our waist, this is our shoulder, this is our elbow, and roll pitch yaw is here. Now, there is a difference between the human arm and this robot arm. So, in this robot arm the 3 axes are intersecting. This is very, very important, that the last 3 axes are intersecting. Okay. Okay. Now, this condition is very, very important, because if it is not intersecting, then we will not be able to have a closed form solution. So, as we do our inverse kinematics, we will see that. So, talking about the equivalence of the human arm and this PUMA robot arm, if I just show it with respect to my hand. So, if you look in terms of our own hand, then this is my waist axis. We can consider this to be our waist. Okay, this is my waist axis, and the arm can rotate about the waist, okay, like this. So, my waist axis is here and the arm is rotating like this. So, this is my Z0, Z1. Okay. Next is this is my shoulder axis, which is my Z2 axis. So, the arm can go up and down like this. So, this, if you can see the axis here. So, this is my axis which is pointing outward on this plane. So, this is Z2. Z3 is the elbow axis, which can rotate like this. So, the axis is pointing outward like this. So, this is my Z3. Now, Z4 is the roll axis, which is here for the robot, okay, and Z5, this is the roll. So, and this is the pitch, and this is the yaw, okay, for the robot. Now, in the human hand, the roll axis is from here. Okay, so, we have a combined elbow joint. So, in the human case, the roll axis comes here. Okay. So, in the human, we have a different wrist, where the last 3 axes are not intersecting. Okay. So, please note that in the case of the robot, the last 3 axes are intersecting at the joint, at the wrist, which is my roll, pitch, and yaw. They are all intersecting here. Whereas, in the case of the human hand, they are not intersecting, because we have the roll which takes place from here. Now, in the human arm, we have 3 degrees of freedom, because this is a ball and socket joint. So, we have 1 axis, 2 axis, and the 3rd axis. Okay. So, we have 3 degrees of freedom at this joint. We have 2 at this joint, which can close like this and can rotate. So, 2 degrees of freedom here, and 2 more here. So, this is my pitch and that is my yaw. So, I have 3, 2, 2, that is 7 degrees of freedom. So, there are some differences with this PUMA robot, which we should keep in mind. And from the point of view of kinematics, this is very, very important, because if you have 7 degrees of freedom, again you do not have a closed form solution. Okay. And as I was mentioning, that the last 3 axes have to intersect, otherwise we do not have a closed form solution. So, let us proceed from here. We have assigned our axis. Now, let us assign the DH parameter table. So, this is my DH table for this robot. So, there are 6 degrees of freedom. So, we have 1, 2, 3, 4, 5, and 6. Where are the joints? 0, 1 is here, 2 is here, 3 is there, 4, sorry, 3 is, this is 3, this is 3. So, 4, 5, 6 are at that point. Now, please note this very, very carefully, that where are the origins of the frame. So, the first 0, 1, and 2 are here. The third fellow is here, which means that there is some distance between this. So, there is a distance in this direction, okay, and there is a distance in this direction between the frames. So, there is a distance here. So, there is a distance here and there is a distance here. Okay. Now, you come to distance between the 3rd axis and the 4th, 5th, 6th. 4th, 5th, 6th are here, but 3rd is here. So, if you look at the distance, there is a distance in this direction, plus there is a distance in that direction, okay, and this is marked A3, that is marked D4. So, please note where the origins are, and the origins are not on the same plane. So, please note what are the distances in the x, y, or z direction. That indicates where the position of the next origin is. Now, let us proceed with our DH parameter table. Our DH table is written this way. So, for the 0 frame and the first frame, so 0 and 1 are here, the 0 and 1 z axis are the same axis, right. Then what about the x axis? The x axis are also the same axis. So, 0 and 1 are, the origins are same, the z's are same, the x's are same. Now, when the first frame moves, or when the first frame rotates, what will change? The angle between x0 and x1 will change, right, which is my theta 1. Okay. So, if you can imagine, if x0 is in this direction, when it rotates, x1 will come this side, and that is my theta 1, if you can imagine that, right. So, in the first case, it is alpha is, let us write down here, alpha is the angle between the z's, okay. A is the distance between the z's, okay. Di is the distance between the origins or the x's, sorry, distance between the x's, and this is the angle between the x's, okay, just to remember. So, this is the angle between the z axis, okay. This is the distance between the z axis, this is the distance between x axis, and this is the angle between the x axis. So, for 0 and 1 frame, this is 0 frame, 1 frame. What is the angle between the z? It is the same axis as you can see here. So, there is no distance between them. So, there is no angle between them. So, essentially the distance is angle is 0. Now, if you look at the distance between the z axis, again is the same angle, there is no angle between them, is the same axis, and there is no distance between them. So, it is 0 there. Now, if you look at the distance between the x axis, now the x axis x0 and x1 initially are the same axis, and hence there is no distance between them, it is 0. Now, when this moves, when the link 1 moves, what would happen is the relative position, relative angle between the x0 and the x1 will change. So, this is my x1. So, this angle is going to change, and hence the variable here is theta 1. Okay. So, that is how we got our first, that is how this is the first row of the DH parameter table. Now, the second row is the relation between the second axis and the first axis. Okay. Where is the second axis? The second axis origin and the first axis are the same. So, they are at this point, but Z2, there is an angle between Z2 and Z1. Now, Z2 is here and Z1 is there. So, there is an angle of 90 degrees between them. Okay. So, what is the angle between the Z axis, which is alpha? So, the angle between the Z axis is 90 degrees. Now, if you can just imagine that if Z1 was pointing in this direction, it rotated by 90 degrees clockwise about the x axis and became Z2. Now, clockwise rotations by convention, if you say clockwise rotations, rotation about the x axis is taken as negative, okay, just convention. Okay. So, so clockwise rotations about the z axis is taken as negative. So, this clockwise rotations about x axis is taken as negative. So, if you can imagine Z1 was in this direction, it has become Z1 was in this direction, it has gone in that direction. So, it has rotated by 90 degrees clockwise about the x axis. So, this is my x axis, it is rotating clockwise about the x axis and becoming Z2. So, because it is rotation is 90 and it is clockwise, so it is taken as minus. So, as per convention, we look in this direction. So, we look in this direction, okay, towards the origin and decide whether it is clockwise or anti-clockwise. So, in this case, you can imagine yourself standing here and the origin is there, you are looking towards the origin, and in that case this is a clockwise rotation, and hence it is minus. Now, the distance between the z axis, now Z2 and Z1 are again the same axis, right. If you can see Z2 and Z1, they are meeting at this point and it is the same axis. So, there is no distance between the z's and hence it is 0. Okay. So, Z2 and Z1 are the same axis and there is no distance between them. Now, if you look at the distance between the x axis, again x1 and x0 are the same axis, sorry, x1 and x0, x1, x2 are all the same axis, and hence again there is no distance between the x, they are all meeting at the same point there. Now, if you look at the angle between the x axis, then when this arm moves, what will happen is it is going to rotate like that, if you can imagine. Now, when it rotates like that, what will happen? The angle between the x1 and the x2 will change. Why? Because x2 is going to come up or it will go down. Okay. So, it can go down or come up depending on it is clockwise or anti-clockwise about Z2. Okay. So, in that case the variable here is theta 2. So, if I draw x2 this side now, so this was my x1, x2 has come down and this is the angle theta 2 there. Okay. So, that is the angle theta 2. So, the variable is theta 2 here. Now, looking at the relation between the third frame and the second frame, which is the third frame and the second frame, the relation between them. So, where is the third frame? The third frame is here. Where is the second frame? It is there. Okay. Now, what is the distance, what is the angle between the z axis? Again you can see that the Z2 is in this direction, okay, and Z3 is in this direction and they are parallel. Okay. Now, because they are parallel, there is no angle between them and hence it is 0. Now, if you look at the distance between the z axis, there is a distance between the z's now. So, this is my distance between the z's, and what is the distance between the z's? It is given by A2. Okay. So, A2 is the distance between the distance between the z's. So, A2 is marked somewhere here. Okay. It has got a little clumsy, but so the distance between this axis and this axis is given here as A2. okay, and that is the distance between the z. Now, what is the distance between the x axis now? Now, the distance between the x axis, there is one origin is here, another origin is there. So, if you were to imagine this origin has moved like this along the y direction, and then it has gone like this and come here. So, there are two distances, one distance is this one, the distance here, and the other distance is this distance here. Okay. So, this we have covered as A2. So, this is my A2. Okay. Now, this distance is the one that is D3, which is written here as D3, the distance between this origin and that point is now my D3. Okay. And if when the link 3 rotates either clockwise or anticlockwise, what will change? The angle between the x3 and the x2. Okay. So, theta is the angle between the x2 axis, which is pointing in this direction, and x3 is here. So, when the axis 3 rotates, what will happen? Theta 3 is going to change. Now, we can come down and look, so we can come and look at this the figure here, okay, which for completing the table. Now, when we look at this table, when we look at this link, the enlarged view of this link, my axis 3 is here and axis 3 is here on this figure. Axis 4, 5, 6 are here. Now, again you can see that there is a distance there, there is a distance here and there is a distance there. Okay. So, there is a distance between the origins. So, what is the relation of 3 and 4? So, essentially you can see that Z3 is in that direction, okay, whereas X4 is in this direction. So, what it means is that there is an angle between them. Now, if you see the rotation about the x axis, then x3 is rotated by 90 degrees in the clockwise direction about the x axis, right, and hence it is a minus 90 there. Okay. And so, if you can imagine again, you are standing from here and you are seeing that it is being rotated like in this way, okay, about the x axis clockwise, and Z3 is becoming Z4. Okay. So, Z3 was in that direction, if I draw it here, Z3 was that side, it is becoming Z4. Okay. So, it is rotating by 90 about this axis in a clockwise fashion. So, this is my this is my Z3. Okay. So, this one becomes a minus 90. Now, what is the distance between the z's? So, Z3 is here, Z4 is here. Now, what is the distance between them? There is a distance of A3 now. Okay. So, this is the distance. So, this is my A3. So, there is a distance between the z axis. Now, what is the distance between the x axis? That is my D. So, where is the x axis? The x axis of Z3 is upward, and the x axis of Z4 of axis 4 is here. So, there is a distance, this much is the distance, and what we get is D4, which is the distance D4. Now, when axis 4 moves, what will happen is the angle between the x is going to change, and that is my theta 4, okay, the variable theta 4. Now, we come to the wrist. So, this is 4 and 5. Okay. Now, if you look at 4 and 5, Z4 is in this direction, okay, Z5 is in that direction. So, how it has moved? It has rotated 90 degrees anti-clockwise now about the x axis. So, it has moved like this, okay, because of which this is 90, but it is positive. Again, all the 3 axes are intersecting at the wrist, and hence you can see the distance z between the distance between the z axis to be equal to 0. Okay. Distance between x axis is also 0 because they are all intersecting at the same point. Now, when axis 5 rotates or moves, what will happen? The x axis, the angle between the x4 and x5 will change, and that is my variable theta 5. Okay. Now, moving on to the last link, that is 5 and 6. So, if you look at the 5th and the 6th, so Z5 is in this direction, and Z6 is this way. It is along the Z4. Okay. So, again there is an angle of 90 there, but now if you see the rotation is clockwise about the x. Okay. So, this Z5 rotates clockwise about the x axis and becomes Z6, and hence this is a minus 90. Now, the origins are intersecting, origins are the same, and hence there is no angle between them. Okay. There is no distance or angle between the z axis or the x axis, and when the 6th joint moves, what would happen is the angle between the x5 and x6 is going to change, okay, and that is my variable theta 6. So, out of all these variables in this DH parameter table, we see that the thetas are the variables, okay. Everything else is fixed, okay. It is 0 or it is 90, or these are lengths A2, A3, D3, D4, these are all lengths, so they cannot change. So, this gives us the DH parameter table, and from this DH parameter table we have to next make the transformation matrix, which will relate frame 1 to frame 0, then 2 to 1, then 3 to 2, then 4 to 3, 5 to 4, and then 6 to 5, and then multiply them out to get the relationship between the last frame, that is the 6th frame, with reference to the 0 frame, okay. Now, how do we proceed? What we do here is we simply take each row of this DH parameter table, okay. So, I take the first row and put it in the generalized matrix. So, I have a generalized matrix which we had done in the last class, where I can relate the I minus 1 frame to the ith frame, and I simply take these values and put it into this generalized matrix, and I get my matrix T0 to 1. Then similarly, I take the second row, put it in the generalized matrix, and get my second transformation matrix, then third, fourth, fifth, sixth, in that order. And if you do that, what we do get is our transformation matrices relating one frame to the other frame. So, we have the first one, which is relating 0 to 1, then we have 2 to 1, 2 to 1, then we have 3 to 2, 4 to 3, 5 to 4, and then 6 to 5, okay. Now, what we need to do is I need to multiply all of them together, okay. But something to note here is that if we multiply all of them together and get our final matrix T0 to T6, okay, I will be multiplying all of them together, okay. If you do that and then try and solve the inverse kinematics, then it is not possible to solve, okay. Why? Because what you would see in the next few slides is that essentially, because there are so many sine and cos terms. Now, the moment there are sine and cos terms, what would happen is each term will have, each cos and sine will have two solutions. Now, there are 6 thetas, so there are 6 sine and cos, and they appear in all combinations, okay. So, what would happen, for each case you have two solutions, and they are going to appear in all different solutions, and you know that solving an equation having the sine and cos terms which are coupled with one another is extremely difficult, okay. So, we do not multiply 0 to 6 straight away, but we multiply in a reverse order. Now, this is the reverse order in which we are multiplying. So, let me write it here. T0 to 6 is given by T0 to 1, then T1 to 2, and then T2 to 3, T3 to 4, T4 to 5, and T5 to 6. Okay, this is the way it is. So, instead of multiplying straight, what we do is we multiply from this side, okay. Now, why, it will become clear as we go along. So, essentially we are multiplying the first two first. So, I am multiplying these two, so which is given here 4 to 6. So, 4, 5, 5, 6, when we multiply the two matrices, which are the two matrices? So, this one and this one I am multiplying. So, first, and I get this matrix. So, you know how to multiply. So, multiplication is very straightforward once you get the matrices. Then what we do is we multiply with, so this is my first, these two, then I multiply with this one, this is second, okay, and this is 3 to 6. So, I simply take 3 to 4, multiply by 4 to 6, and what I get is this one, okay. And then what will we do? We will multiply 1 to 2 again. So, what we do is we multiply 1 to 3, okay. So, let me come here. So, first I multiplied this these two, okay. So, let me so first we multiplied these two, okay, 5 to 6, okay. This is the one we first multiplied. Then I multiplied it with we multiplied this one first, okay. So, we get 4 to 6. Then I multiplied this with 3 to 6, okay. So, I multiplied with 3, so I got 3 to 6. So, I multiplied with this one now, okay. So, we get 3 to 6. So, this is first, this is second, 3 to 6, okay. And okay. So, we get 3 to 6 from here. Next, what we do is we multiply these two, 1 to 3, okay. I multiply these two. So, first, second, third is this one separately, and we multiply this separately, 1 to 3. So, it is 1 to 2 and 2 to 3, and then I combine all the, and then I combine the full one. So, I multiply this into this, and what do we get is this matrix 1 to 6, okay. So, we get this matrix 1 to 6. So, so here is my 1 to 6 matrix. So, this into that is T 1 to 6. Okay. Now, if you are wondering why we did that essentially and why we left out this fellow, okay, because it was observed that if you multiply it out like this 1 to 6, your final matrix 1 to 6 matrix comes out like this, and each of the terms, for example R11, R11 essentially is this one, R11 is the first term, and it comes out like this. These are the terms which are contained in R11, and if you see, this is actually cos, this is cos theta 2 plus theta 3 into cos theta 4 into cos theta 5 into cos theta 6 minus sin 4 sin theta 4 sin theta 6. Okay. So, this one minus this term here. Okay. So, this is minus sin of theta 2 plus theta 3 into sin theta 5 into sin theta 6. Okay. So, it is written in short, but this actually 2 3 means theta 1 theta 2 plus theta 3, and again here it means theta 2 plus theta 3 here. Okay. Now, because these terms are appearing like this, it will be extremely difficult to solve, that you know that these are trigonometric equations appearing in all combinations. So, if you look at all the terms and we try and equate the left hand side of the desired matrix with that of the final matrix between the end effector and the we will not be able to solve. So, what I mean is, if I multiply 0 to 6, so I get 0 to 6 here, okay, and this is my desired position plus orientation matrix for doing the inverse kinematics. Okay. If I take term by term and try and solve, so this is a 4 by 4 matrix, this is also 4 by 4, but if I take term by term, these are all the terms, right. So, if you take term by term here and try and solve, it will become extremely difficult to solve, or you will not be able to solve. Why? Because you can see that cos and sin are appearing in all kind of combinations here. Now, if you see terms which do not have sin and cos, okay, or they have the least number of sin and cos, then maybe it is a good idea to try and solve from there. And if you see some of these terms, we have one term here P1y, which is this term P1y is this one, which only has a d3. Okay. That means there is no sin and cos here, and d3 is a constant. Okay. So, all other terms have at least 2, say this one has sin theta 4, sin theta 5, the other ones have even more numbers of cos and sin involved, right. So, if we try and solve from here, okay, start our solution process from here, then we might be able to solve. So, what I am saying here is, we take this element from here, this is the third element here, the element here which is coming, which is this one, okay, sorry, this will not come here. Okay. So, if we take this element and then try and equate it on the other side, we may be able to solve, but please note that this is 0 to 6, this one is 1 to 6, which means that I have to remove theta 1 from here. Okay. So, I have to remove theta 1 from this to bring it to this form. Okay. Then I can try and start solving. So, what we do is, if I want to remove theta 1 from here, I simply multiply I take theta 1 from here, that is the first matrix T 0 to 1, take its inverse and bring it onto that side. Okay. Now, if I bring it onto that side, what it essentially means is that I have 1 to 6 on this side now. 1 to 6 would mean that the variables are now theta 2 to theta 6. Okay. Theta 1 has gone this side now. Okay. So, that is the basic philosophy, or the process for trying to solve for the PUMA. We observed that if you multiply 1 to 6, this transformation matrix 1 to 6, then you end up with a term which is P1y, which only has a d3 there. Everything else has a sin and a cos. So, we start from here, and what we do is, this is my 0 to 6 matrix. Okay. So, 0 to 1 and 1 to 6 is given by here. So, if I want to remove this, what I can do is, I can take it that side, right. I can take the inverse and take it that side, and that is essentially what we try and do. So, we take the T 0 to 6 matrix, okay, and multiply it with the inverse of T 0 to 1, this is the inverse matrix. So, what it essentially does is, it is removing the first variable, okay, and on the right hand side we have T and on the right hand side we have T 1 to 6, right. So, this is my this is our equation T 1 to 6, and you know what is T 1 to 6? T 1 to 6 is this one is T 1 to 6. Okay. So, this is our T 1 to 6 that we have got here. Okay. This is my T 1 to 6 which is here. Okay. Now, what we do is we know what is this matrix. Okay. How do we know what is that matrix? That is essentially what is T 0 to 1, what we got here. Okay. So, I simply take the inverse of this. You know the inverse of transformation homogeneous transformation matrix. We just take the transpose of that, and we take the transpose of the transpose into minus of this one, right. That is the negative, or that is the inverse of this matrix. So, I find the inverse, multiply it here. Okay. So, this is my inverse of that, and we multiply it with this T 1 to 6, and I get 1 to 6. Now, next, if you see, so this was T 0 to 1 inverse, and this is my T 0 to 6. Okay. So, what we do get now is, if you multiply this out, what you get is equating terms. Now, this is equation 4.56. Okay. Now, if you equate this one, okay, Py which was D3, so this fellow was D3. Okay. Now, if you equate this with the second term of this matrix, so I take this and multiply with that, what we do get is minus of sin Px plus this is S1 Px plus cos 1 Py is equal to D3. Okay. So, I take this and I multiply with that, and then equate this side with that side. Okay. Then what do we get is we get this one equation, right. So, what we are doing here is I am multiplying, I am simply multiplying this row with this one, because I want to equate this term, okay, of this side of the left hand side with that of the right hand side. Okay. And what we get is this term. Now, you see that this is one equation, and this is a constant, and it has one variable. Okay. Only theta 1 is the variable. Okay. So, now because theta 1 is the variable, we were able to solve it, and we can solve it by making the substitution. Px is equal to rho times cos phi, and Py is equal to rho times sin phi. And making the substitution, we can find theta 1 to be a tan 2 Px Py minus this formula. Okay. So, here we have found what is theta 1. Now, I hope you understand why it was done this way, and something to remember here is that we multiply 1 to 6, because only under that condition this one term here does not have a sin and a cos. Okay. And the whole solution procedure is based on the fact that if we remove the theta 1 from the left hand side of this, what would happen is it is like removing theta 1, and you end up with one term. You can get one equation where you can equate this into that with this side, and you are able to get only one variable, one equation, one variable, and then we can solve it. Okay. Otherwise, we can't solve it. So, once you get theta 1, next is what we do is, if we equate both 1 4 and 3 4 elements from the two sides of this. So, 1 4 and 3 4, let us see what is 1 4 and 3 4. So, 1 into 4 is this one, okay, 1 4 element, okay, of this side. So, this is 1, and into that is the fourth one from this side. So, 1 4 we are going to equate on both sides, and 3 4 we are going to equate on both sides. Okay. So, 1 4 and 3 4. So, you can imagine this is C1 Px and S1 Py is my, so you will be getting this term, and on the right side it is this term. On the right side also it is going to be your the 1 4 element on 1 6, which is this one. So, what is the 1 4 element on so the 1 4 element is going to become here. Okay. So, it is this one. Okay. 1 4 element is going to become this one. So, we are going to equate this term with this into that, and what we get is this equation. Two equations we get. So, for the 1 4 term we get this one, equating 1 4 on both sides we get that, equating 3 4 on both sides of this, again we get this equation. Again 3 4 would mean 3 4. So, it is 3 and it is 4 again. So, if you equate it, what we will get is this equation. So, this equation, what do we know here? We already know theta 2. Sorry, what do we know from here? We know theta 1 we know. So, what we know from here is theta 1 we know, Okay. Now, this has how many unknowns? This has theta 2 is an unknown here and theta 3 is an unknown, right. So, we just found out theta 1. So, what is, we have a theta 3 and we have a theta 2 and a theta 3. So, there are two equations and there are two unknowns, and we can try and solve them. So, if we square and add both these equations, what we do get is we can get theta 3 like this. Okay. So, we have got theta 1. So, in the previous case we got theta 1, now we are getting theta 3. This equation contains theta 2 also, so we can solve also for theta 2. Okay. Now, next what we do is, so from here we can get theta 1, theta 3 and theta 2 from this set of equations. Next what do we do is we equate the 1 4 elements and the 2 4 elements from the two sides of 470 from this equation. Okay. What we essentially do is we multiply by the inverse of 0 to 3. Now, if you are multiplying with the inverse of 0 to 3, what is happening is this 0, theta 1, theta 2 and theta 3 are getting removed. Okay. So, on the right hand side you only have this terms 4, 5 and 6. Okay. So, this 3 theta 1, theta 2, theta 3 are gone now. So, this equation is only in terms of theta 4, theta 5 and theta 6. And now, so this is our matrix. Okay. This is equation 4.7, and if you are equating the terms again 1 4 element and 2 4 elements from the two sides of this. So, 1 4 again would mean this into that with the 1 4 element on this side, 2 4 would mean 2 into this equating with the 2 4 element on this side. Okay. So, if you equate them we get another two equations, and this gives us two equations and two unknowns, and we are able to solve it here. So, here we are able to solve for theta 3. Okay. So, theta 1 is solved here. Okay. Theta 2 is theta 3 is solved here. I need to solve for theta 3. So, what we do is essentially we are getting the solution for theta 3 here. Sorry. So, we are getting the solution for theta 3, and then we proceed to get solutions for theta 4. Okay. So, from here we can try and solve for so we can solve for the sum of theta 2 plus theta 3, from which we can take out what is theta 2. Okay. So, here I have already got theta 1 theta 3. So, here I can take out what is theta 2. Okay. Now, proceeding similarly, now the entire left hand side of 470 is known. So, equating 1 3 elements and 3 3 elements from two sides of this, we get two equations again, and now I can get from here I can get theta 4, then correspondingly we can get theta 5 and then theta 6. Okay. Theta 5, similarly equating elements 1 3 and 3 3, we can get theta 5 and then we can get theta 6. So, essentially we are able to get all the solutions of theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6. Okay. But something to note here essentially is that the solution procedure entails that we do not when we are multiplying we have to be careful that the order in which we are multiplying, we do not multiply the total matrix, we do not multiply the 6 matrices together, but we multiply them in stages or in groups. So, this is my first group, this is the second group, and that is essentially done because if you do it like that, then you end up with one term here P1y which has only one which does not have a sine and a cos. So, this is the point to start from, and how do we start from there? We basically take this equation, okay, and bring it to the form. So, if I multiply it like this, what would happen? It will come to the form 1 to 6, okay, and then we equate terms and try and find. So, first we find for theta 1, then we find for theta 3, then we find for theta 2, okay, then we find for this is for theta 2, then for theta 3, sorry, theta 3 is already found, then theta 4, then theta 5 and then theta 6. So, essentially going term by term we can find for all of them. So, this is the general inverse kinematic solution. So, this is the inverse kinematics solution for the PUMA robot. Okay. And now, if you are thinking a little bit as to why this condition of having the last 3 axes intersecting is very very important here, is if you are trying to figure out that why did we solve it like this, or is there any other way of solving it. So, if you go back again a little bit, it's asking the question the question that is relevant here is, why did this happen? Why did it happen that this term, okay, had only a d3, did not have a cos and a sine associated with it? Okay. And if you think a little bit and look into the structure of the robot, why is it important that the last 3 axes are intersecting here? Okay. So till here you can see that 1, 2, 3 we have, so till here, okay, you can see that there is the link lengths changed, so A2 and A3, and we also have the offset distances which are changing d3 and d4. But after this there is no change here and there is no change here, okay, and that is because the origins are the same. Now if the origins were not the same, then for example if I had the origin of the 5th frame somewhere here and I shifted it here, then what would happen? A distance will come here, okay. So what would happen is you would end up with a distance between something here and something here, okay. In that case what would happen is the structure of the final structure would not be like this, because some other element would get added onto this now, okay, and we will not be able to have the same structure as the structure that we are getting here. So it is very, very important that the last 3 axes are intersecting, because when they are intersecting, beyond this point there is no change here and there is no change here, okay. And in the human arm that is not so, because in the elbow, our elbow and our elbow has a roll, and the last 3 axes are not intersecting, okay. That makes it impossible to solve, or the human arm does not have a closed form inverse kinematic solution. So this is the standard way of solving for the PUMA manipulator system, and after this what we need to see is, so the important part to note here is inverse kinematic solution of PUMA, and the most important part, so let us put 2 or 3 stars on that, is that the last 3 axes are intersecting, okay. So this is very, very important that the last 3 axes have to intersect, okay, otherwise this solution will not work anymore. Now the next thing we need to look at is what we call the relationship. We need to look at the Jacobian, which gives the relation between the joint velocities and the end effector velocities. So what is the relationship between the joint and the end effector velocities, and why is it important? Let us just understand how a robot works, then it will become clear. So we have one link here, we have another link there, and we have another link here, okay. So far we have only looked at the kinematics, but now let us look at how does the robot actually work. So we have a joint, and the joint is going to be actuated by a motor. So there will be a gearbox in front and there will be an encoder at the back, okay. So similarly here also there is going to be a motor, gear, and an encoder, and this type of actuation is called independent joint control, where every joint has a gear, actuator, and an encoder. So this is called independent joint control. Now this is my variable theta1, okay, this is my variable theta2, and that is my variable theta3. What is the end effector coordinate here? So we can say the coordinate of this point is x, y, z, okay. In this case, because it is planar, there is no z, so let me just write x and y, okay. So now how does the robot actually move? So what we do is, if you want to move the end effector, say I want to move from here to here, how is it going to move? Essentially inverse kinematics will tell me that at this location, at this position and orientation, what is the new theta1 dash, then it will do theta1 dash minus theta1, okay. So by using inverse kinematics I am going to find the difference between theta1 dash and theta1 and make that into some kind of an error of theta1, okay. And then what we will do is we are going to actuate the motor. How are we going to actuate the motor? We are going to actuate the motor by giving a voltage, okay, when we are using pulse width modulation, when we are using a PWM control. Then we are going to give a voltage to the motor. When I give a voltage to the motor will rotate. If the motor rotates, then the joint is going to rotate. If the joint rotates, then the the end effector is going to move. Okay. So, essentially the sequence by which it goes is you give a voltage to motor. After you are giving a voltage to the motor, because of which the joint is going to rotate, so we will get some velocity at the joint, and because the joint is moving, okay, we will get some change of end effector velocity x dot y dot. Okay. So, essentially we have different spaces. What I mean is, on one side you have the motor which is running by a voltage. Okay. So, this is my voltage space, okay. This is volts. Okay. Then if you give a voltage to the motor, it rotates, the joint rotates. So, this is my theta dot. So, this is theta dot is polar coordinates, okay, which is theta in degrees or in radians. So, this is polar. Then finally the end effector moves, this is xy, which is my Cartesian space. So, we see that there are three spaces, the voltage space, which is unit of volts, this is polar, it can be degrees or it can be radians. This one is xy, x dot y dot, which is basically Cartesian space. Now, if I am giving a voltage here, some voltage here, it is creating some angular velocity, and if it is creating some angular velocity like this, okay, so different voltages will create different angular velocities. Now, if I am going to give a particular joint velocity, it will create an end effector velocity, right. So, now what I am interested in seeing is, are there mappings, is this, what kind of mapping is it? Is it 1:1 mapping? Is this fellow going nowhere? For example, there is also a null space, so is it going into the null? Okay. So, what it basically means is, I want to see the mapping between different spaces. Why this is important? Because it gives an indirect measure of the energy also, okay. And if there are places where the robot cannot go, that means there is no mapping between them. So, if there is no mapping, then essentially the robot cannot go there, and that is called a singularity. Okay. So, singularities are basically places where the end effector cannot go, essentially because there is no relationship in this mapping. And this is also interesting that sometimes you can give a joint velocity, but there will be no end effector velocity. So, where did that velocity go, or where did the energy go? So, that went into the null space. Okay. So, that went nowhere. So, that also happens. So, this mapping is very, very important, and this mapping is governed by what we call the Jacobian. Okay. So, today we will stop here. In the next class we will be starting off with Jacobians, which basically relates the end effector velocity. So, it relates the joint velocity at the joint and the end effector velocity. So, this is related by the Jacobian, and it determines a lot of things, like for example, whether it is possible to go, what is the energy required, and if it is singular, where the manipulator cannot go. So, next class we will be starting off with Jacobians. So, we stop here today. Thank you.